We have misunderstood the ocean. Those are not my words. Those are the words of researchers at the Nippon Foundation and the General Bathymetric Chart of the Oceans, a global coalition of scientists, navies, and governments who have spent the last decade trying to do something that sounds embarrassingly simple. Map the bottom of the sea, not another planet, not a distant moon, the floor beneath the water that covers 70% of our own world. And after nearly a decade of coordinated international effort, after deploying research vessels across every ocean basin, after contributions from over 185 organizations in dozens of countries, they have mapped 27%. 27% of Earth. We have better maps of Mars. We have better maps of the far side of the moon. We have a more complete topographic picture of Venus, a planet wrapped in sulfuric acid clouds, 400 degrees hot, than we do of the ground beneath the Atlantic Ocean. And that is not a metaphor, it is a measurement. And the deeper you look into why that number is so low, the more unsettling the answer becomes. Because the problem isn't funding, it isn't logistics, it isn't a lack of interest. The ocean is actively, physically resisting our attempts to understand it. And what we've found in the small fraction we have mapped is already forcing scientists to question things they thought were settled decades ago. This is not a small problem. For most of modern history, the deep ocean was treated as a footnote. Scientists assumed it was a vast, cold, mostly empty desert, and the logic seemed airtight. Sunlight doesn't penetrate below about 200 meters. Without sunlight, there's no photosynthesis. Without photosynthesis, there's no food chain. Without a food chain, there's no meaningful life. Step by step, the reasoning held. The deep sea was, in every model, a graveyard, a dark basement beneath the productive surface, maybe a few scavengers picking through falling debris, maybe some bacteria clinging to sediment, but nothing that would rewrite a textbook, nothing worth building a fleet of ships to go find. This belief wasn't unreasonable, it was based on the tools we had. Early oceanographers lowered weighted lines off the sides of ships and counted the meters of rope. That was the technology. That was how we measured the depth of an ocean that averages nearly 4 kilometers deep. The first real map of the ocean floor wasn't produced until the 1950s, when Marie Tharp and Bruce Heezen spent years piecing together sonar readings from Navy vessels to draw what the Atlantic seafloor actually looked like. When Tharp plotted the data, she found a massive rift valley running down the center of the Atlantic. Her own colleague dismissed it. The idea of a split in the ocean floor didn't match the science of the time. She was right, and the discovery helped confirm plate tectonics. But the point is this: as recently as 70 years ago, the most basic structural features of the ocean floor were unknown. Not the details, the structure. And what we've learned since then has come in fragments, scattered across expeditions decades apart, often by accident. Then came multi-beam sonar, and everything changed. Not because the ocean got simpler, because it got incomprehensibly more complicated. What we found did not confirm our understanding, it complicated it. In some cases, it contradicted it. And the deeper we've looked, the wider the cracks have become. The trouble starts with a number, not a depth, a speed. A research vessel running multi-beam sonar covers roughly 150 square kilometers of seafloor per day when mapping deep ocean. The ocean floor spans approximately 361 million square kilometers. Run the numbers and you get a campaign that would require a single ship to operate continuously for over 6,500 years. Obviously, you don't use a single ship. But even with the entire global research fleet, the maths is staggering, and the fleet isn't dedicated to mapping. These vessels have other missions, other funding, other priorities. The ocean simply isn't a place where you can point a camera and zoom in. Sound is the only tool that works in deep water. And sound is slow, it's methodical. It requires a physical ship above the target area, burning fuel, fighting weather, and crawling forward at survey speed. And this is where things stop making sense. Satellite altimetry, the technique used to estimate the remaining 73% of the seafloor, doesn't actually see the bottom. It measures the height of the ocean surface. Massive features on the seafloor, like underwater mountains, exert a slightly stronger gravitational pull, which creates tiny, measurable bumps in the water above them. A depression on the seafloor creates a dip. NASA's SWAT satellite, launched in 2022, has improved this technique significantly, detecting features with centimeter-level accuracy and sea surface height. But here's the catch. Surface altimetry can detect large features, seamounts, ridges, trenches. It cannot detect anything smaller than roughly 1.5 kilometers across. And the ocean floor is not made of large features. It's made of millions of abyssal hills, volcanic formations, fracture zones, hydrothermal vents, and sediment channels, most of which are far smaller than satellite resolution can resolve. They exist. We know they exist. But from orbit, they're invisible. 2 methods. 2 pictures of the same seafloor. One assembled with acoustic precision down to 100 meters. The other interpolated from gravity signals 1,000 meters above. They should agree. They don't. And the gap between them isn't academic. It's the difference between a map you can navigate by and a sketch made from orbit. That might sound like a technical inconvenience. It is not. Because the things we're finding in the map 27% are changing our understanding of the ocean in ways that nobody anticipated. In 2024, a team of Chinese researchers aboard the submersible Fendouzhe descended into the Kuril-Kamchatka Trench, one of the deepest points on the planet, nearly 10.5 kilometers below the surface. They expected bacteria, maybe a few amphipods. The standard model said this was a dead zone, pressure exceeding 1,000 atmospheres, total darkness, no known food source for hundreds of kilometers in any direction. That's not what they found. What they found were thriving colonies of tube worms nearly a foot long, alongside mollusks, crustaceans, and sea cucumbers. Not at a hydrothermal vent, not near any known energy source. In a place where sunlight hasn't reached in billions of years, these organisms were sustained by chemosynthetic communities, bacteria that convert hydrogen sulfide and methane leaking through faults in the trench floor into energy. No sunlight required, no connection to the surface food web whatsoever. This shouldn't be happening, not at this depth, not at this scale. The discovery, published in Nature in 2025, documented the deepest and most extensive chemosynthesis-based communities ever found on Earth. Not a single vent site, not a small cluster, an ecosystem spanning 2,500 kilometers of trench floor at depths between 5,800 and 9,500 meters. An entire food chain running on chemistry instead of light, buried under kilometers of water in a place nobody had ever bothered to look properly. And that's where the scientific conflict begins. One camp, led by deep-sea ecologists who have spent decades studying the Hadal Zone, argues that these chemosynthetic communities are likely widespread across all major trench systems, and that we've simply never had the technology to find them before. If true, the energy budget of the deep ocean, the total amount of biological activity happening below the sunlit zone, would need to be revised upward. Significantly. Some estimates suggest the revision could be an order of magnitude. That's not a tweak, that's a rewrite. The other camp pushes back, hard. They point out that the Kuril-Kamchatka Trench sits in a subduction zone where tectonic activity drives methane and sulfide to the surface through deep faults. Not all trenches have that geological setup. Generalizing from one trench system to all Hadal environments, they argue, would be premature and potentially misleading for the models that depend on accurate energy budgets. Both sides are credible. Both are careful. Both are looking at the same data and arriving at different conclusions about what the ocean is telling them. And that's the core of the problem. We're trying to build a theory of deep ocean life from fragments of a map that is barely a quarter complete. It's like trying to diagnose a patient when you can only see one of their limbs. But the story didn't end there cleanly, because the discoveries kept stacking. In the same year, research published in Cell revealed that the Mariana Trench alone harbors over 7,500 newly identified microbial species, nearly 90% of which had never been documented in any public database. Think about that for a second. One trench, 7,500 species nobody knew existed. An entirely new superfamily of amphipods, the Mirabestioidea, was described from the Clarion-Clipperton Zone, a massive abyssal plain in the Central Pacific. Not a new species, not a new genus, a new superfamily representing a completely new branch on the tree of life. In waters off Argentina, a a canyon twice as deep as the Grand Canyon was found teeming with siphonophores, translucent colonial organisms drifting in currents where two ocean masses collide. And at Monterey Bay, a gelatinous creature that had been spotted occasionally for over 20 years was finally identified. It turned out to be a nudibranch from an entirely new family, something so different from known sea slugs that it required a new taxonomic category to describe. Each of these findings came from the mapped fraction. Each was a surprise. Each required scientists to adjust what they thought lived where and how. And all of it came from the 27% we've actually looked at. At that point, the model starts to bend. Some of the early alarm about deep-sea biodiversity has been tempered. When extensive mapping of the Clarion-Clipperton Zone identified nearly 800 species at 4,000 meters depth, many assumed the numbers proved the deep sea was as rich as a tropical rainforest. A closer look told a more complicated story. A significant portion of those species were rare, localized, and extraordinarily vulnerable. A deep-sea mining trial in the same zone reduced animal abundance by 37% and species diversity by 32% in the tracks of the mining machine. The ecosystem was real, but it was fragile, not a rainforest. More like a very old, very slow library where every book is an original, and nothing has a copy. Damage it, and what you lose doesn't grow back. Not in a human lifetime, possibly not ever. Not enough to break the model, enough to bend it. Because here is the broader implication, and this is where it matters beyond the ocean. The deep sea isn't just unexplored. It's unexplored in a way that undermines the confidence of every model that depends on it. Ocean circulation models, which predict how heat moves around the planet and how quickly the climate responds to carbon emissions, depend on accurate bathymetry. If the shape of the seafloor is wrong, the simulated currents are wrong. If the currents are wrong, the heat transport is wrong. And if the heat transport is wrong, the climate projections shift. Not in a catastrophic, headline-grabbing way. In a quiet, systemic way that makes everything downstream slightly less trustworthy. Every forecast, every policy built on top of those forecasts. Tsunami early warning systems depend on knowing the depth and shape of the ocean floor between the earthquake source and the coastline. A seamount that isn't on the map can refract a tsunami wave in ways the model doesn't predict. That's not a theoretical concern. It's a public safety failure waiting to happen in 73% of the ocean. Undersea cable routes, which carry 97% of intercontinental internet traffic, are planned using bathymetric data. Cables laid over unmapped terrain face risks from underwater landslides, volcanic activity, and sediment flows that nobody knew were there, because nobody had looked. And then there's the question of carbon. The deep ocean is the largest active carbon sink on Earth. It absorbs roughly a quarter of all human CO2 emissions. But the mechanisms by which carbon reaches the deep seafloor, how it's stored, how long it stays, and how microbial communities process it, are still poorly understood. The discovery of extensive chemosynthetic communities in Hadal trenches means methane cycling at extreme depth may be far more active than current models assume. If methane hydrates are widespread in trench sediments, the global inventory of methane, a greenhouse gas roughly 80 times more potent than CO2 over 20 years, may need to be recalculated. We can't recalculate what we haven't measured, and we can't measure what we haven't mapped, and we haven't mapped 73%. The Seabed 2030 project knows it won't hit its target. The name was always aspirational. At the current rate of mapping, roughly 4 million square kilometers per year, completing the remaining seafloor would take decades, not years. Autonomous surface vessels and underwater drones are accelerating the work. NASA's SWAT satellite is improving the resolution of gravity-based estimates. New AI tools can process sonar data faster than human analysts. But the fundamental constraint remains. The ocean is deep, sound is slow, ships are expensive, and the seafloor doesn't care about our deadlines. What's remarkable about this moment in ocean science is that the frustration is productive. Nobody is panicking. Nobody is giving up. The prevailing mood is closer to the feeling you get when you've been assembling a jigsaw puzzle for years, confident you had the picture right, and then you find a piece that doesn't fit anywhere. It doesn't mean the puzzle is wrong. It means the picture on the box might not be the whole picture. That's the thing about crises in science. They feel like failures. They almost always turn out to be doors. If you could somehow stand outside the Earth and watch this moment, you'd see a species that has mapped the surface of Mars to a resolution of 6 meters per pixel. A species that has photographed a black hole 55 million light years away. That has landed robots on comets and driven rovers across another planet's craters. And that species still does not know what the bottom of its own ocean looks like. That's either absurd or magnificent. And I think it might be both. The ocean isn't hiding from us. We just haven't built the tools to see it yet. And every time we lower a sonar into water we've never measured, every time we send a submersible into a trench nobody has visited, we find something that wasn't supposed to be there. Something alive. Something complex. Something that doesn't fit the models we built from the surface. The floor beneath our feet, beneath our ships, beneath the weight of every ocean on this planet, is not what we drew on the map. It never was. And the next version of that map, whenever it arrives, is going to be stranger and more alive than anything we've imagined so far. Thanks for watching, and I'll see you in the next one.